Welcome back. I'm hoping everybody's having a great weekend, or you had a great weekend and now you are involved into the week. Now we're moving into a new phase of the lecture in regard to intermolecular forces and the effects that we see, like vaporization, viscosity, and so on. Specifically on this part, we are going to talk about calculations to determine the amount of heat released or absorbed when something vaporizes or condense. And we also can see, based on the energy that we need, what mass or amount of matter we can condense or evaporate. So we're going to be doing calculations in relation to vaporization, but also to condensation. Because when we have a molecules on a liquid and we apply heat to it, and I'm going to do it with a triangle, that will mean heat, which is nothing more than thermal energy. When we apply to it, so a plus, the molecules will start moving faster, and because of that, they separate, which is what we call the gaseous state. But if we take energy away, then the molecules begin to slow down, and when they slow down, if they happen to be dipole molecules, then they have a higher possibility that the proper orientation will happen and the intermolecular force will grab hold and bring them together. And we call that condensation. So we're going to call this process going from left to right vaporization, and from right to left, which is the opposite, we call it condensation. Similar thing with freezing and melting, but we're going to talk about that on the next lecture. So how can we apply math or do calculations in relation to mass and energy? Well, let's see. Let's start with this problem. Which causes a more severe burn? Spilling 0.50 grams of water at the boiling point on your hand, or allowing 0.50 grams of steam to condense on your hand? And why? Well, let's visualize the situation. You have your hand, and we're spilling hot water into it, and it's really hot water at 100 degrees Celsius, compared to having your hand and sending steam, which is at 100 degrees Celsius also, into your hand, and the steam then condense into water. So, which one will hurt you more? Which one will make you cry? And we have to see that in terms of the energy that is going to be released into your hands. Because if energy is released into your hands, then the molecules of your hands will start moving faster, and that will start destroying your skin, your proteins, your DNA, anything there. Basically, you're getting a high degree of burning condition. So which one will be worse? Hot water or steam? If you remember from chapter 3, I believe, we can calculate the amount of heat by knowing how much mass is involved, the change in temperature, and the heat capacity of the water. Since we're talking about water in both of them, then the heat capacity is irrelevant because it's the same for both of them. On the first one, the water is at 100 degrees, So we're talking 100 degree waters, and it's coming into your body, and your body is around 97 degrees, something like that. It fails my memory right now. So your human body temperature is less than 100. Actually, that would be Fahrenheit, right? So a lot less than 100 degrees Celsius. So there's going to be a change in temperature. It's going to go from the hot water temperature to your hand temperature. So we're going to see a change. On the other case, and we are assuming, and we know the mass of the water is the same, so the mass is not a factor. So on the first change, it's only once the water touches your hands, the difference between your body and the water temperature has to equilibrate. So the energy always travels from the hot body to the cold body. So your hand is going to receive that energy. That's what's going to hurt. What about the steam? Well, the steam is condensing. So what is the change of temperature when it's something condensed? There's really not change of temperature. I don't know if you remember from chapter 3 also, when I showed you if you have ice and the ice melt and then the water vaporizes, the ice melt at 0 degrees Celsius, but it freezes also at 0 degrees Celsius. Water boils at 100 degrees Celsius, but it condenses also 100 degrees Celsius. So what I'm saying is, when you have a change of state, like gas going to liquid, which is what's happening precisely here, the gas is going to liquid, there is not a change in temperature. So we got a problem. We're trying to compare the energy of a process that involves a change in temperature, like the water going from 100 degrees to equilibrating with your body, to a process that does not involve a change in temperature. So how do we calculate? How do we compare? Well, there's something new that we haven't discussed. We didn't cover this on chapter 3, and it's a new formula to calculate the heat or the energy involved when there's a phase change, when it goes from solid to liquid or liquid to gas or gas to liquid and liquid to solid. So when there's a phase change, we are not longer using the formula you learned on chapter 3. Now we're using a new one that involves the amount times the enthalpy of vaporization. So enthalpy refers to the amount of energy that something contains, and we are talking specifically, on this case, going from steam to liquid. So we call that condensation. The opposite is vaporization. So we call that amount of energy the enthalpy of vaporization, which have been determined by scientists through the years. And for water specifically, if we're talking about the boiling point, 100 degrees Celsius, which is what we're talking on this problem, right? Then for every 1 mole of water, you're gonna have to absorb, if you're going from liquid to gas, or release, if you're going from gas to liquid, 40.7 kilojoules. If the water happens to be at room temperature, then the amount is going to be a little bit different. It's going to absorb, it's going to need more to get to that point. Remember that water can vaporize at any temperature, right? It just vaporizes more at higher temperature. So the value that we're going to use for water at boiling point is going to be 40.7 kilojoules. So let's see how we're going to use that. So what we're gonna do is we're gonna say, I know that it's gonna be 40.7 kilojoules for every 1 mole. I know I'm dealing with 0.50 grams of water. And as you notice, this is nothing more than a conversion factor. So we are able to use a train track, but to do that, you're gonna have to cancel the grams first because you need moles, which basically means you're gonna be able to transfer your grams, you're gonna have to cancel your moles, and that's gonna give you kilojoules. So we know that 1 mole of water equals 18.0 grams. So you can go from the amount of water, which is, or steam on this case, 0.50 grams. You can change that to moles, and then the enthalpy of vaporization for water at 100 degrees is 40.7 kilojoules per mole for every 1 mole. So then you can use that conversion factor to find your kilojoules. So when we do all that, we're gonna see that on the first one, there's gonna be a change in temperature between your body and the water. And then you're gonna multiply that. So you can calculate how much this energy is. But this formula will tell you how much energy a change of phase releases. So we're gonna find out when we do those calculations that the steam condensing on your hands is gonna definitely send you to the hospital. The water, not as much. So the amount of energy that you're gonna see coming from the steam is gonna be huge compared to the water, to the amount of energy coming from the hot water just touching you. And I'm gonna let you do those calculations so you can compare the numbers on your own. So let me summarize this here. So the main thing we're learning is that energy in the forms of Q can be calculated when there is a change of phase. And every time I say change of phase, think ice becoming water, water becoming gas. So you're gonna have melting, and then you're gonna have boiling, or you can have condensation and then freezing. And melting and freezing happens at 0 degrees Celsius. Condensation and boiling happen at 100 degrees Celsius. So when there's a phase change, there is no change in temperature. So the formula that you used to see to calculate thermal heat, which is this one from chapter 3, requires a change in temperature. So a phase change, there is no change of temperature, so you cannot use that formula. So the formula that we're gonna use whenever there is a change of phase or a phase change is gonna be the amount, which can be grams or moles, depending on how the value is given. On this case, the delta H of vaporization is given on kilojoules per mole, so this will have to be moles. For other tables, you're gonna see kilojoules per gram, so in that case, you can use grams. So the amount of energy that is released when there's a change of phase involved is huge compared to just a change in temperature. So keep that in mind. So once more, the enthalpy of vaporization for water at 100 degrees Celsius is going to be 40.7 kilojoules for every 1 mole, which is nothing more than a conversion factor, where you have two units that you can relate. So let's do another problem. So that one told us comparatively how to understand the concept. What about this one? How much heat is required to vaporize? So vaporize is going from liquid to gas, so the molecules have to move faster and separate. So this one is gonna require energy. We're gonna need to add energy. So how much is required to vaporize 43.9 grams of acetone at its boiling point? Obviously, we need to have additional knowledge. So we're gonna look for acetone. We're looking for the boiling point. The boiling point is 56.1 degrees Celsius. And the heat of vaporization that we're looking for is not 25 degrees, it's the one at the boiling point. So 29.1 kilojoules per mole. So I know I'm gonna be I'm looking for how much heat, so I know I want heat at the end. Units of heats are gonna be kilojoules. And I know I'm beginning with 43.9 grams of acetone. So how do I go from grams to energy? Well, the process is vaporization. So I'm gonna have to use 29.1 kilojoules. That way I have kilojoules already at the top for every 1 mole. However, I do not have moles, so I'm gonna have to fix that. I'm gonna begin my train track by getting rid of the grams, because what I need to get rid of eventually is gonna be the moles. And this is nothing more than the molar mass. So 1 mole of acetone, I would have to know what acetone is. I got the formula right there. C3H6, C3H6O, which means 3 times 12.0 grams per mole, 6 times 1.0, and 1 times 16.0, which is nothing more than 36, 42, 58. So 58.0 grams. So when I do this calculation, let me go ahead and do it this time. I'm going to be multiplying 43.9 times 1 times 29.1 divided by everything at the bottom, which is going to be 58.0 grams. So that's going to be 22.0 kilojoules. So everything else cancels except the kilojoules unit. So that's how much heat I'm going to need to apply to 43.9 grams of acetone for it to vaporize. So let's do the second one. How much is emitted? So now we are releasing heat. So we are releasing heat when 4.20 grams of water condenses. So condensing means that the molecules that are gas are going to have to slow down so that the intermolecular forces grab on and go from gas to liquid, where the molecules are closer together. And this is happening at 25 degrees Celsius. So let me clear the screen. So I'm looking for my water at 25 degrees Celsius. And it's going to condense. Remember, condensation is just the opposite of vaporization. So we're still going to be using the heat of vaporization. Positive if it's vaporizing, negative if it's condensing because it has to release energy. So we're going to use this value, 44.0 kilojoules for every 1 mole of water. And because it's condensation, I need to know that condensation, the molecules come together, they have to slow down, so they have to release energy. So I need to know that it's going to be negative based on my knowledge of the kinetic molecular theory of gases and all that kind of stuff. And I'm beginning with 4.21 grams of water. Immediately I can see that I'm going to have to do something there because those units are not going to cancel. So I'm going to get rid of the grams first and make it 2 moles so I can cancel my moles. And I end up only with kilojoules because the question is find the heat. So that's kilojoules. And I'm talking about water. So 1 mole of water equals 18.0 grams, right? 1 oxygen and 2 hydrogen, 16 plus 1 plus 1. And grams will cancel with grams, moles will cancel with moles, and all I have left is my kilojoules. So for me to be able to condense 4.25 grams of water, so 4.25 times 44 negative divided by 18, I'm going to have to be prepared to receive, because it's going to be releasing that amount, 10.4 kilojoules of energy. So that's a good way to warm up my house, right? If I have a steam and I can get it to condense, it will release energy into my house, therefore warming up my house. That's how a radiator works. So look into that later so you can see, oh, so that's how a radiator or a heater works with water. That's how air conditioning works. And most recently, you have probably seen this portable air conditioning where you add water to it. So that water takes the water vapors that is around you, which can be probably hotter, and the exchange of temperature with the colder water allows that to condense, and that will release energy that would be like a heater. Or when that water gets vaporized, it's because it's absorbing energy from the environment, so that would be like an air conditioning because it's cooling the air around you. So all these engineers would use to design instruments like that. So with that said, you should be able to do these problems. There's 2 parts to it. Remember, these problems are nothing more than dimensional analysis or conversion factors using train track, and your values are given there in 2 units that you can interchange. Just be careful. Make sure you know at what conditions you're working and the substance you're working with. So go ahead and work on that one. And once you're done with that one, we can say that pending more practice in Alex, we are now knowledgeable. And we're just looking for mastering with practice on how to do calculations involving vaporization or condensation, which is the opposite process. Condensation will require energy, vaporization will require energy, condensation will release energy. And when you're done with that, when we meet again, we will go through the same logic, but this time we're doing it with melting and freezing. So solid to liquid or sublimation, solid straight to gas. So until the next time, see you soon. Take care.